I will cover one last, we will come back to hyperparameter tuning and model selection, but now that we have more tools, more concept to understand these, we will see it again. So the main question is, can we verify this? Can we see if there is a difference between the real risk and the empirical risk? But we don't have the real data distribution. That's the main problem. And the validation set and the test set will be quantities that will estimate it, and the training set will be used to find the model that will minimize the empirical risk. So I don't want to rely on this estimation of this quantity, because you see that HS is the optimal point to minimize LS. And of course, there is a HD that will be the optimal model that will minimize LD. Since we don't have D, we cannot find it. But we will simulate it. We will use another set called validation set for hyperparameters that we will use to estimate this quantity. And if the gap between the two is huge, probably the gap between the real risk and this quantity is also important. And so if you deploy your model, the performance that you will observe will probably be closer to the validation, to the performance on the validation set than the one that you obtain by choosing the model that minimizes the empirical risk. And it's computed, so the validation set is defined similarly than the training set, and the loss is computed exactly in the same way. You use the same loss function, and you take the empirical average over the set V. And since we have an iterative algorithm for the optimization, you will monitor the two values. You will monitor the empirical risk in red, which we will call the training error, and you will monitor an estimation of the risk with the validation set that we will call after that the validation error. And this is typically the shape of the two curves that you will observe in many of your experiments in deep learning. At the beginning, the model is performing badly on the two sets, and at some point, you will see the curve of the validation error that will increase. It means that at this point, the model begins to memorize, to cheat, to use features that are only relevant in the training set to minimize the loss. And so it will continue to decrease, but these features are not useful to generalize, and so the validation error will increase. And what we probably want to do is to do several checkpoints along this curve, so you will save the model parameters on your disk, and you will stop the training before the validation error increases too much. It's called early stopping. And so you will retrieve the model parameters evaluated here, instead of retrieving the parameters only at the end of the training. And if we come back to our experimental protocol, now I can define several model family. So maybe a very one-layer neural network, 2 layers neural network, a convolutional neural network, etc. I define different families of model. Each family will have a set of parameters where the optimizer will navigate inside. And I will find for each family the model inside the space, H, that will minimize the empirical risk predictor here. And then I will evaluate each of these models on my validation set to retrieve the performance, to retrieve an estimation of the risk. And so this one has the best performance on my validation set. And again, maybe because I'm optimizing, I'm looking for the best model according to the validation set over many, many experiments, maybe I can still overfit the validation set. It's more tricky to understand, but it can happen. I will use a final test set to be sure that the performance here is close to the performance here. Is there a huge gap? Then there may be a problem in your experimental protocol. You should investigate more. So the take-home message of this presentation is that machine learning is very broad. There's a lot of different techniques, different models, different algorithms in machine learning. The statistical learning framework helps us to understand more what is overfitting in terms of a probability distribution defined over the examples. A model can be too biased, too simple, not enough complexity, or can have too much variance, where there's a lot of complexity, but because I don't have enough data, the decision boundaries are arbitrary. And we saw that data is necessary but not sufficient. And finally, deep learning is a very efficient way to define complex hypothesis class that, and we don't know still the answer, but deep learning empirically generalize better than other models. And this is a very active research topic today to understand why these architectures minimize the gap between the empirical risk and the real risk. And here I put some references so that you can have the math but done properly. It will have required more than 1 hour to cover this concept, but I used this book to inspire myself for this talk. Thank you very much.